Qualitative and quantitative analysis of solutions. Okay, or substances. Qualitative analysis is a technique or practice used to determine if an element is present in a given material, or even an ion. Element or ion is present. For example, gas tests can be used to determine the presence of gases. If you do a glowing splint test, if oxygen is present, the splint relights. If you have hydrogen gas, you hear a high-pitched pop. Precipitation reactions can be used to determine if an ion is present in solutions. And there are some really nice schematic diagrams online that show how to do this. You can add a particular reagent to your solution, and if, let's say, chloride ions are present, you will precipitate out a white precipitate. So you can identify your the ions present. Colors of solutions or flame tests can be used to determine if an element or ion is present. For instance, copper 2+ makes blue clear solutions. Flame tests are really cool, and you can basically heat a sample over in the hottest part of a Bunsen burner flame, and you will get discrete colors for the elements. This is a really nice flame test color chart put out by Compound Interest. This gentleman is a high school teacher, and he's made a lot of infographics, and if you follow the link, it'll take you right to the website, but it's pretty accurate. Quantitative analysis is a process to determine how much of a substance is present or how much product theoretically can be produced in a reaction. Sound familiar? A great deal of chemistry takes place in aqueous solutions for a number of reasons. Water's cheap, readily available. It dissolves many substances. It's the universal solvent. Faster reactions occur because the chemicals can mix more completely when they're dissolved. It's easier to control reaction speeds by adjusting the temperature or reactant concentrations for the reaction. Being able to predict the quantity of product or quantity of reactant required is critical for the success of many chemical processes. For example, water treatment. You need to know how much of a treatment to add if you've got a problem in your water. You don't want to add too little or too much. Hospital IV solutions need to have certain concentrations in order to treat someone properly. Whether it's medication or for dietary needs, you need to be able to correctly figure these out. So stoichiometry will allow us to determine yields and limiting reagents just like we did before with gravimetric analysis. The only difference will be that we start with concentration and volume rather than mass and molar mass. So we're going to do a couple of examples. The first two aren't reactions, but they're basic review. If 100 milliliters of a 2 mole per liter solution is diluted to 1 liter, what is the new concentration? So this is a dilution question. So this is our first volume. This is our first concentration. And this is our second volume. We want to find the new concentration. You could, instead of V1 and C1, use concentrated, so VC, CC. And then the new 1 liter and the new concentration are dilute, so you could use a D. Okay, so because the moles before and the moles after for the solute are the same, the only thing we're doing is adding water. We're not adding solute. So C1 V1 equals C2 V2. We want to find the new concentration, so we want to isolate C2. So if we divide both sides by the second volume, we will have a formula we can use, and then you just plug in your values. So first concentration is 2. Now we have milliliters, 100 milliliters. So you have to convert that to liters first. And there is 1,000 milliliters per liter. So we're going to times this by 0.1 liter divided by 1 liter. So the new concentration is 0.2. Our liters cancel, but not our values. So 0.20 moles per liter is our new concentration. So it's really important that you remember how to dilute a substance and get a new concentration. Example number 2. If 20 milliliters of 0.10 mole per liter sodium chloride solution is mixed with 50 milliliters of 20 mole per liter solution, what is the new concentration? Again, this is another dilution question. You will not get a reaction if you have two solutions with the same anion. So we have the same substance here. So we have 20 milliliters, and we add 50 milliliters. So change those values to liters first. So we have 0.020 liters, and we have 0.05 liters. Okay, so here's our volume. We're mixing. This time we are mixing two solutes together. So we will change the number of moles of solute. We're not adding water, we're adding another solution. So we have to figure out how many moles we have in each beaker ahead of time, so we know how much is there when we add them together. So moles is going to be equal to the concentration times the volume. So this one is 0.1 times 0.02. And then this one is 0.2 times 50 milliliters, or 0.05 liters. So we will have decimal 0.002 moles, and we will have 0.010 moles. Now we've added these together. So we're literally going to add these together. So the total moles is the sum of these two numbers. So we have 0.012 moles of solute. The total volume has changed now too. We've added 50 milliliters to 20 milliliters. So we have a total of 70 milliliters. So now we'll might as well add them as our liters. So we have 70 milliliters, or 0.07 liters. Now our final concentration is our total moles divided by our total volume. So 0.012 moles divided by 0.07 liters. So this gives us a concentration of 0.17 mole per liter. So when we mix these two solutions of sodium chloride together, we end up with a concentration that's somewhere between. That makes sense that a low number plus a high number will equal a medium number. So we end up with a final concentration of 0.17 mole per liter. This is a situation where you might be just taking different samples and amalgamating your solutions so that you free up bottles and storage containers. All right, here we go. Determine the minimum volume of 0.42 mole per liter sodium sulfate that is required to react completely with all the barium ions in 500 milliliters of 0.1 mole per liter barium chloride. All right, so let's first of all, just like we did before, write down what we know below the substance. So we know we've got that concentration. The volume we're trying to figure out. Barium chloride, we have 500 milliliters. So if we convert that, that's equal to 0.5 liters. And we know the concentration. So we're not asked about any product. All we want to know is how much volume we need of sodium sulfate. So to do that, we need to know how many moles of sodium sulfate we will need, because C is equal to N over V. If we're looking for V, we have to know C and N. But we don't know N. However, barium chloride, we have C, we have V, we can find N, and then use stoichiometry mole ratios to figure out the moles of sodium sulfate. Okay, so to figure out the moles of barium chloride, it's the concentration times the volume. So 0.1 mole per liter times 0.5 liters. So 0.05 moles. And that's barium chloride. So now we need to figure out how many moles of sodium sulfate that will represent. So we're going to convert to sodium sulfate from barium chloride. Barium chloride is going to go on the bottom so that it cancels. The mole ratio is 1:1 for the coefficients in the balanced chemical equation. So we have 0.05 moles of sodium sulfate. So now we've got moles, we can figure out volume. So volume will be equal to moles divided by concentration. So 0.05 moles divided by 0.42 moles per liter. Our moles are going to cancel. And this quantity is equal to 0.119 liters. If we round that off to two significant digits and multiply it by 1,000 to get milliliters, this is going to be equal to 120 milliliters. So we would need 120 milliliters of our sodium sulfate solution to react with all of half a liter of 0.1 molar barium chloride. Okay, predict the mass of precipitate expected when 1.5 liter of 0.8 mole per liter sodium sulfide is mixed with 850 milliliters of 1 mole per liter aluminum chloride solution. All right, so let's place what we know where we know it. So sodium sulfide is 1.50 liters, and the concentration is 0.8 mole per liter. Aluminum chloride, 850 milliliters. Convert that to liters, and we have 0.85 liters and 1 mole per liter. All right, and we need to figure out the mass of precipitate. So our aluminum sulfide is our precipitate, so we need the molar mass of this, 2 times 26.98, and 3 times 32.06. So that's 150.14 grams per mole. Put that in here, 150.14 grams per mole. Okay, so we've got to figure out how much mass we can produce from sodium sulfide, how much mass we can produce from aluminum chloride, see which one produces the least amount, because that is going to be our limiting reagent. The reaction stops once that reagent is all used up. So we need to find moles. So moles is equal to concentration times volume. So for sodium sulfide, 0.8 mole per liter times 1.5 liters. So that's 1.2 moles of sodium sulfide. So now convert that to moles of product. So we want to go to aluminum sulfide from sodium sulfide, and the mole ratio is 1 to 3 from our coefficients of our balanced chemical equation. Sodium sulfide cancels. So we have 0.4 moles of aluminum sulfide. The mass you find by taking the moles times the molar mass. So 0.4 times 150.14 grams per mole. Moles cancel. And that gives us 60.056 grams. So that is from sodium sulfide. Now we're going to do it again, but we're going to do it for aluminum chloride. So moles is equal to concentration times volume. So we take our concentration times the volume, and we get 0.850 moles of aluminum chloride. So now we're going to multiply this by our mole ratio, which is 1 aluminum sulfide for every 2 aluminum chlorides. So 0.425 moles of aluminum sulfide. So we can see we're going to have less mass of this. So this one's the one in excess. So moles times molar mass, 0.425 moles times 150.14 grams per mole equals 63.8095 grams. So the smallest mass comes from the limiting reagent, so our sodium sulfide is going to get used up first. So we can produce, and we can have 3 sig figs. No, 2 sig figs. So we will produce 60 grams of aluminum sulfide. That will be the maximum mass of precipitate. So that should give you some idea of calculations we can do with solutions. So it's very similar to what we did with gravimetric stoichiometry. And we'll give you some practice questions.